share my screen now. Hopefully you can see that. And I've got a version of Python there as well with some code that I haven't, my last push didn't get to. Okay, let's see if I can work out how to do this as a presentation. Menu on the top left, because of course it is. Where else would the menu be? Window. Or present, come on. No, full screen mode. There we go, that'll do. Here we go. Okay, so list comprehensions, generator expressions, and functions. And it's trying to do transcription in the window. That's terrifying. I'm really sorry about that. Okay, right. As usual, sorry about that, a lot of rambling. If you have any questions as we're going or comments, do feel free to ask. Okay, so we're starting, our starting point is iteration and for loops. Here is a very standard for loop shown. Let's do that in Python. This is a nice feature of Python. We've got a list of tuples, so technically a nested data structure. This is all about working with data, this session. List comprehensions are a great way of working with data fluidly. So here we've got a list of tuples there. Every tuple here represents a point. So they're x, y coordinates. And we can do that tuple unpacking in the loop. So we can do for x, comma, y in points. And here both x and y are the iteration variables. So every time through the loop, x and y are going to get new values. So the first time through, they'll get 3 and 4. Second time through, they'll get 5 and 7. So that's tuple unpacking in a loop. Tuple unpacking is a lovely language feature. We'll see it again when we look at functions. And that's straightforward iteration. We take something that we can iterate over. So so we can see that the type of points is list. This is the list literal syntax. But points isn't iterable, something we can iterate over. So there's a couple of built-in functions that are really nice, help us when we're working with iterables. Another thing that's worth looking at is the itertools library, some really nice components there you can put together when iterating. Enumerate is built in, it's part of the standard library. And it's really common that when we're iterating, we want to keep track of where we are in the loop. So for example, let's do OSDR list dir. Let's see where we are. Let's do with open temp.py. Let's open this file and open file handle in text mode. We can loop over a line at a time. So let's start with an x equals 0 with open temp.py. I have no idea what's in temp.py. Hopefully as a file handle for line in H. We want to keep track of the line we're on. If there's an error, we want to report the line number. So we're keeping track. We're going to increment. So this means we'll start at 1, and then we can print. We'll print X, which is our line number. We'll print the line, and every line will be new line terminated already. So we won't print an extra new line afterwards. Let's see. And there's nothing in that in temp.py. So let's open temp.py. Write some text. .write. Hello. New line. Goodbye. New line. Another line. New line. There we go. Relying on garbage collection to close the file handle for us. And now when we repeat this whole thing, Slash h, but we can see the line number has been updated every time we've gone through the loop. X plus equals 1. We've been keeping track of that position in the iteration itself. Turns out we do that sort of thing all the time. It's very common. And then you've got the ever so minor mental overhead of, do I increment my counter at the beginning or at the end? And if I'm doing it at the end and I've got some continues, then there are a few branches where it needs to be updated. So this little use case of keeping track of where we are in an iteration, enumerate does it for us. And enumerate gives us a nice little illustration of iterating over pairs. So, for example, we've got here names, Elwood, Jake, and Curtis. We want to loop over these. We're going to use enumerate to help us loop over them. So, enumerate names. Names is some iterable. What this gives us is an enumerate object. It gives us something we can iterate over. It's not a list. It's lazy. It's something we can fetch things from one at a time. And if we do this, so let's do it. Let's call it I for item. If we iterate over E here, our enumerate object, next simulates one loop through an iteration. It's a useful little trick. We get one item from it. What do we get? We get an item of pairs. So each pair is going to be comprised of this position in the iteration as an integer and an item from the iterable. So the first one is going to be 0 and Elwood. And if we call next again, no need to spit in an intermediate variable. We're going to get 1 and Jake, and then 2 and Curtis. If you're interested in this iteration protocol and what happens with iteration itself, there is a knowledge sharing session on generators, I think, which covers this and covers next and iter and the full iteration protocol. Okay, so that's enumerate. So enumerate produces pairs one at a time, but it's more common to do the unpacking in the iteration itself. So it'll be for I, that's the index position, and then the item itself in enumerate. So we don't usually see those pairs. So it's name, really. There's enumerate. Enumerate, it's a nice little shortcut. And also we're introducing this concept of iterating over pairs. I'm going to the next built-in function we're going to use to combine iterators. This, as we move into list comprehensions and generator expressions, these are ways of working with data, processing and transforming data, and combining iterators with other corresponding iterators is something we do very commonly when we're working with data. Okay, so enumerate is a nice shortcut. This is how we use it for I, X in enumerate, and this is the code it's exactly equivalent to. Nice and straightforward, hopefully. Does that make sense to everyone? Yeah. Gabriel, what do you think? I can see you. You're muted. It was very unfair to pick on you. Sorry.
No, that's all right. So initially on your first example, we had some tuples, right? I don't know. I don't remember if it was on your... Yes, there. So a mistake that I did not once or twice, a few times. So try to iterate over something that doesn't really has any tuples and adding X and Y. So if I use enumerate, I can loop over a list, a simple list with, I don't know, strings. And I will be able to use X and Y and have my index because I have enumerate.
We're feeding in names. The iterable we're giving to enumerate, it's a sequence. It's a sequence of one thing after another. Here it's a sequence of strings. So, but what enumerate does is it creates these pairs. It creates essentially it creates an iterable of pairs, an iterable of tuples, each with 2 entries. And so we can use this syntax in the loop to unpack it.
Cool. Thanks.
Thanks, Gabriel. Okay, so the next one is the zip function. And it's very often that we get sequences that correspond to each other, particularly when we're processing something like row-oriented data. Now, databases, spreadsheets, CSVs, they all store data in a row-oriented fashion. So when we're working with a CSV or with a database or spreadsheet, each of the columns has meaning. So the columns here, name, amount, and price, this is from a CSV file. These column headers apply to every single row, so we can combine them. So let's bring up the interactive interpreter. These column headers are name, amount, price. If we've actually read this from a CSV file, this might be the first row in the CSV file, the headers. The headers are optional, it's part of the CSV spec, such as it is. We might have the values from an individual row, so a name of chair, an amount of 100 as an integer, and a price of 47.59. Moderately expensive chair, reasonably cheap, I guess. So obviously, first entry, index position 0 columns, that corresponds to index position 0 in values, and similarly, index position 1 in columns corresponds to index position 1 in values. They're lined up. So we can use zip to combine these sequences, to put together, to pair up the corresponding entries. So again, that produces a zip object, lazy rather than eager. If I call next on pairs, what's the first thing that's going to come out of this? Does anyone want to guess? Able to guess?
Name chair?
Yeah. Nice. Next one, Gabriel.
Amount 100.
Yes. And finally, I know you were paying attention. Price, yeah, 47.59. So these pairs with column headers, name, chair, amount, 100, price, 47.59. These pairs, if we think of one of our data types, the dictionary, the hash table. The hash table is the data structure under the hood. The dictionary is how we use it. If you call dictionary.items, you get a list, or at least certainly a sequence of tuples, of key value pairs. And we can think of a dictionary as a collection of key value pairs. So the dict constructor will take a list of key value pairs and turn it into a dictionary for you. So from the headers and the values, we can zip those together, produce key value pairs, and there's a really concise bit of code for turning individual rows into dictionaries, changing the data type. Zip is a nice little standard library function. It does turn up in all sorts of interesting places. Now, the trouble with zip, zip will combine arbitrary number of sequences. So here I can use it, I can zip together columns, values. We've got some tags that apply to the columns. And now when I call next on, pick a name to that, call next on Z. Now I'm going to get, because I put 3 input sequences in, I'm going to get tuples with 3 entries each time. However, there is what is now considered a deficiency in the standard, the default behavior of zip. If I give it, if one of these sequences is shorter than the others, by default, zip silently just truncates everything to just 2 results. So we get the first one, the second one, the third one, we've got price and 47.59, but there's no, the tags sequence that I gave, it only has 2 entries. We're going to find this iterator is now exhausted, and zip doesn't warn us about the fact that they don't all match up. It's most common to use it when they all line up. We can pass the strict equals true keyword in, I recommend that you do that every single time. And now we'll get an exception. And we want that exception because probably this tags list being short is a bug. And we want to be notified with it.
What would happen if you, can I just ask a question?
Yeah.
What would happen if you made a dictionary out of those sort of data structures with 3 values rather than 2?
What you would be doing would be passing to the dict constructor a sequence of tuples where every tuple has 3 entries, and the dict constructor will say, I don't know what to do with this.
Okay.
It works with sequences of 2 tuples. So rough will now warn you. We're using rough as a code quality checker on many of our projects. Now it will warn you if you use zip without an explicit strict keyword, and I recommend using strict equals true unless you really know that it doesn't need to be strict. So that's zip. Is that any questions on that? Comments, observations? Cool. So list comprehensions. List comprehensions are a lovely, concise bit of syntax for doing filtering and transformation in a single expression. So let's say we've got a list of numbers and we want to work out the square of all of these numbers, because that's an obvious thing to do when you've got a list of numbers, right? 1, 3, 4. One way of doing that, get a results list, create an empty results list for num in A. So we're going to create the result, that's num squared. We're going to do results.append result, and that will construct a new list with the square of each of the numbers. And there's syntax to do this in one line as an expression. They're really handy, you use them a lot. And the trick to understanding them, if you've not worked with them before, is you start reading them in the middle. So it's an iteration. It's always an iteration, and it actually creates a list. So it's got this square bracket syntax of the list literal. That's telling you it creates a real list.
Michael?
Yes.
You could also compare it as reading SQL, where you have a select where from where.
Yes, yeah, that's right. It's similar to a select. Yeah. And especially with the filtering that we're about to introduce. That's SQL is a more general version. Okay, so this is the for loop. We're creating a results list. We're iterating over A. We're squaring every entry and putting that value into the results. The list comprehension version of this is num squared for num in A. And it produces the same set of results. So we start looking at it in the middle for num in A. That's the iteration. That's the loop. A is the iterable, what we're iterating over, and num is the loop variable. And then on the left is the operation. So num squared is done for every number in A, and it's num squared that gets put in the list and builds the list up. So these 2 bits of code are essentially identical. Functionally exactly identical. Another thing, if you're doing anything with text, it's very common to want to do case insensitive searches or comparisons. So we want a lowercase version of our names, name.lower for name in names. So again, very easy to understand what we've got. We've got lowercase version there. For name in names, we've got a loop. This is what we're iterating over, and name is the iteration variable. For name in names, a name is a string, it's a list of strings, so we're just getting the lowercase version. What we end up with in the result list is the lowercase version. Names itself is not modified. As usual, we're just iterating over it and processing the entries one at a time. So that's the most straightforward, the simplest version of a list comprehension. And if you see them, because they're exactly equivalent of, there is a very simple Python equivalence. They're easy to read. Okay, we can also use a list comprehension to filter, just like a bit like a select as well. We have a list of numbers: 1, -5, 4, 2, -2, -1, apparently 10. We want this to double all of these numbers, but only for the positive numbers, only for the numbers greater than 0. So again, we could write this code: results equals create an empty list for num in A. If num is greater than 0, let's do results.append, and here's the operation. We want to double each number, num times 2. So we've got a loop and a filter and an operation that we're performing. This is the answer we get. We can express all of that in a single list comprehension: a loop with a filter and an operation. So let's start writing it in the middle, and it's for num in A. And now we've got the filter. We only want numbers that are greater than 0. So if num greater than 0, and if the number is greater than 0, then we perform our operation, which is num times 2, and we should get exactly the same results. And we do. Here's another example. Reading an inventory.csv, you can imagine you might be looping over a log file, looking for every line that has critical in it. And the log file might be gigabytes long, but when you open a file handle and you iterate over it a line at a time, you're not holding the whole thing in memory. So this list comprehension will loop over it a line at a time, and every line that doesn't have chair is immediately discarded. So you can search gigabyte files and only keep in memory the ones we filtered out. So this list comprehension here only exists for the filter. There's no operation. We're throwing away lines that don't have chair in them and keeping the rest. So hopefully that's straightforward. John, have you got your hand up again or still?
No, I have still. I was just going to ask, like the map function, then does that do the same thing? Like
it does, yeah.
And when would you use one over the other? I suppose.
Well, the map function was actually removed from the language, and filter was moved out into func tools, and then people because map can always be done with a list comprehension. They are kind of exactly equivalent, but map, filter, reduce are standard elements, components of functional programming. So there was much outcry at them being removed from the core language and sort of treated as a second best. So they are back in the language again. I would almost never use map. What I might do is where I have a list or a sequence of items and I want to apply some kind of, I want to call a method on each of them or something like that. So I'm not building up a result list. I'm performing some kind of transformation or some kind of operation on the whole list. So I'll still keep the list afterwards. So the purpose is not the list that's being built, but the purpose is the operation that's being applied. Then I might use map and discard the return value, because map maps some operation, a callable, onto a sequence, and that might semantically match more clearly what I'm doing than a list. A list comprehension where you throw the result away. I have done it. It's like let's have a look. Where's we might have or something that you can call a method on. Things. Let's have file handles. Let's open temp.py. Imagine these were all different files, and we had a pipeline of files handles that we're processing. You could do h.seek0 for h in things. So seek to the position 0, and then just throw away the results. But it looks a bit weird. I quite like. Here we go. Map. Is a lambda function that calls seek0. So here we're mapping an operation onto the things, except I kind of have to do that. It's still a bit weird. Map is lazy as well in Python 3.
Okay.
I don't use map very often is the short answer.
Okay, thanks.
Okay. So, list comprehensions are in other languages, especially in Haskell. Python and Haskell got them about the same time. It actually comes pretty much straightforwardly from set maths and mathematics. Here's the general syntax, and here's the direct translation of the Python code, what it means. So we have some expression. This is the operation. For names in sequence, you can do 4x comma y in a list comprehension. You can do that tuple unpacking if condition, and here's the arbitrary filter. And it translates to this code. We're building a result list. We're iterating over the sequence. We're applying the filter to every entry. We're applying the expression to every entry, and it's the result of the expression that builds up the list. So that's list comprehensions. They're fundamentally to do with iteration, and we can use them anywhere a sequence is expected. So inside a function call, if you're going to call a function with some sequence, but you need to quickly transform it prior to the function call, you can do it in the function call. It's often a nice, concise syntax.
Is there actually a performance benefit, or is it just for readability?
The bytecode is almost identical to writing the loop out. I think there's a ever so slight performance improvement because you don't have to go back into the interpreter loop quite so many times, but it's very marginal. The bytecode is almost identical. There used to be some differences around the names. I mean, like the one difference is in this code for names in sequence, the names stay around in this scope. So after the iteration is finished, you can still get at names. If you use a list comprehension for X, the X is not visible outside of the list comprehension. So that's the one slight difference. We can do a bunch of stuff with them. Here we've got a list of dictionaries. We can just pull the names out of them. Did I? Yeah, I didn't skip a slide. Good. So we can pull out every item, 4i in items, where the price is greater than 100 and the amount is greater than 50. So taking some data structure as input, running a list comprehension over it, and producing a new data structure as a result. So query-like iterations. And here's a reduction over a sequence. This is like a map reduce, where the operation we map is amounts times price, and then we reduce it to a single value with a sum. This is the cost for all the items, the number of items times their price for every item. So that works out the total cost. For I in items, each item here is a dictionary with an amount and a price. So for every item, if we multiply the amount by the price, we get the cost of that item. So this list comprehension gets us the cost of every single item. That is the input to sum, which reduces this sequence to a single value, the total. It's a map reduce operation. Right, so you've just learned list comprehensions. I suspect for many, if not all of you, wasn't entirely a new concept. The same thing applies for creating sets. There's similar syntax for creating sets and dictionaries. So let's say we've got a dictionary of items. So we've got name equals chair, amount equals 100, price equals 47.59. So that's one item. Let's do another. Name equals table. They're bigger, so we've only got 12 of those in stock. There's some really expensive ones. We've got 456. So we've got a list of items here. This is our inventory. Suppose we want, and in fact, let's append a new item. Let's have some duplicates. Let's have name equals. We'll have another table. We'll only have 8 of these. Amount equals 8. And price equals. These are super expensive tables. So if we get all of the item names, we can do that with a list comprehension like we did before. So we can do item name or item in items. If we look at this, we'll find, because we've got more than one kind of table is duplicated. A set might be a more natural data type to store this in. So if we just use the set comprehension syntax instead, and now I've got a sets are optimized for membership lookups. So if you want some kind of collection of nodes you've already visited when you're walking a tree or a graph, a set is a good collection. So you can very quickly check, have I been here? Have I seen this before? The in and not in operators. So that's a set comprehension. And these are dictionary comprehension, headers and values. So what have we got? Columns. Have we still got these columns and values? We can build a dictionary directly out of that. The syntax for a dictionary comprehension is key colon value inside the same curly braces we use for sets. Key value for key comma value in zip. If we zip together the columns and the values, there's another way of creating a dictionary from them. This is a dictionary comprehension, so it's key colon value for a dictionary comprehension. And this is the set comprehension syntax. Everyone happy with that? Oh, something I missed in.
Could you go over again the difference between the dictionary comprehension and set comprehension? Because the syntax is quite similar, right?
It's very similar. So sets. The syntax for creating an empty set is this. This is the syntax for an empty dictionary. Let's create a set that isn't. So sets are they're a data type that stores a unique list of things. So nums. We're keeping track of numbers we've seen. This is the syntax for a set literal type of nums. That's a set. And now I can do things like I can say 5 in nums. Have we seen 5? No, we haven't. 99 in nums. Yes, we have. Sets are a hash table under the hood. They're constant time. They're very efficient for asking them if something in or not in them. The set literal syntax is like this. So the set comprehension, which is an iteration, will build a set, is, so if we look at items, it's a list of dictionaries. So this is a set comprehension. Every dictionary we're going to pull the name out of. So it's going to be 4 item in items. This is going to pull the name out and it's going to build a set from the names. We've got a duplicate table name. Sets have unique entries only. So we can say, are you there? That false Jerry's in names. That's the set. Dictionary literal syntax is something like item name. Key colon value is the dictionary literal syntax. Name chair. Amount 100. Price 47.59. That's the dictionary syntax, right? The dictionary comprehension is key colon value. And then it's got an iteration. We're going to build the dictionary up one entry at a time. So for key comma value in, we're going to zip together the columns and the values. We're going to use strict equals true because they should match. We want an exception if they don't match. So this is a comprehension that now builds a dictionary. This is the iteration. If I change it into a list comprehension, there has to be a list of tuples. That syntax is no longer valid.
Right. Okay, got it.
But I can do key colon value and build a dictionary instead. It's doing the same loop. At the heart of it is an iteration for key comma value in zip, zipping together the columns and values. There's that iteration, that loop at the heart of it. So it's building the dictionary up one key value pair at a time to make the dictionary. And at the end of it is one dictionary with several key value pairs. And the last thing on this slide is I never used to teach this because I used to think it was too horrible syntax and the world was a better place if I didn't teach it. But I've met a few people who use it and they think I'm a bit of a Luddite. So here we go. This is nested list comprehensions. I try to avoid them. They're perhaps not as bad. They're perhaps not that bad. Here we've got a matrix, so it's two-dimensional list of lists. We want to pull the odd numbers out of these matrices, out of this matrix. So we're going to start the loop for row in matrix. And then for every row, we will also want to iterate over every element. So we then do for elements in row. So we've now got a nested loop. If it's odd, this is a modular. If it's odd, there'll be a 1 left over. And we're just keeping the element itself. So the element for the operation is just element. So there's 2 loops here, for row in matrix, for elements in row. Modulate is division. If element, that's mod 2, not mod 0. If we divide by 2, there's 1 left over, not if we divide by 0. If we divide by 0, bad things happen. There we go. So those are the odd numbers pulled out of the matrix. And that is a nested list comprehension for row in matrix, for elements in row. It's I forget which way around they go if I try and do them myself. I don't necessarily recommend them. Everyone happy with this? Okay, we've got 20 minutes left on functions, 5 minutes of the original time I booked. I'm sorry, we'll do generator expressions in the 45 minutes. Anyone who has to go can go, and we'll move on to functions. So list comprehensions are eager. They have the square bracket syntax. They produce a list. So if you give them something to loop over, they consume that iterable all in one go. The list comprehension syntax is executed and it's done. You've got a list. It's eager. Eager is often what you want. Eager is a good quality. A lot of things are lazy. They don't produce all of their values at once. Range produces numbers. So if we do for I in range 10, it's going to iterate over the numbers 0 to 9. But if I call range 10, it doesn't produce a list of numbers. It produces a range object, an iterable object. We saw the same thing with zip and enumerate. If I do enumerate on nums, it's lazy. It doesn't produce it straight away. This could be a good thing. This can lead to the producer-consumer model. You can have an iterable, an iterator that produces values one at a time, and you consume them one at a time, and it never ends. If you're interested in generators and how they work, programmatic iteration, there's a session on generators and iteration, a video session that I referenced earlier. So Generator expressions are a lazy version of list comprehensions. They look very similar. This is, suppose we've got A, have we still got A? Right, so we have A, we can do a list comprehension that does num squared for num in A, and it's executed straight away, and we get the result. The list comprehension version uses parentheses instead of square brackets. And it produces a generator object, just like normal generators that use the yield keyword. Generators are cool. Go and watch that session if you haven't seen it. Okay, so this is a generator object. It's not called until we start iterating over it. Let's make a really simple wrapper. Generator for I in iterable. We're going to print I and then yield I. So let's do a generator expression num for num in. We're going to wrap nums in a printer. So let's do num squared for num in. And as soon as print is involved, we should see some prints. Nothing happens. There's no prints. That's produced a generator object. If I call next on it, that's going to do one iteration at a time. You can see it prints and then I get the value back. So this is a list comprehension instead of a generator expression. So let's do it the normal way. Results equals, if we call list on it, we'll see all those prints called, and then we get the results. So the biggest advantage of a generator expression over a list comprehension is you don't need the square brackets. So suppose we've got x squared for x in nums. Those square brackets look a bit ugly. The great advantage of generator expressions is now I can do this, and it looks prettier. So this is the primary reason for using generator expressions rather than list comprehension. That's not true. Actually, you may well have a bunch of processing that you want to do in sequence. And if you write it all out as one monster list comprehension, it's going to be too long and really hard to understand. So you're going to break it down into a sequence of transformation steps. You can do all of the intermediate steps as generator expressions, and then the whole thing is only executed once when you finally execute it. Generator expressions are great. They're lazy. Other than that, the syntax is exactly the same as list comprehensions. They can be applied to any iterable, and here, chain together. So for example, here we're squaring every entry in A, then we're negating every entry in B. So we're composing, we're building up a set of transformations as a series of steps in generator expressions, and then in the final for I in C, iterating over the lot. And essentially, this pulls in values from B. When we start iterating the values from B, it pulls in values from A, and we end up with the results here. So generator expressions, just lazy versions of list comprehensions. They produce these one-shot generators. It's a generator object for value in results. I can iterate over it, do nothing with it. If I try and do the same thing again, if I try to iterate over results again, it's now been consumed. This iterator is exhausted. Same iterator, same. So if you understand list comprehensions and know how to use them, there's not really a lot more to say about generator expressions. And that brings us to the time I booked, the 45 minutes. Does anyone want to carry on and do 15 minutes on functions? Will anyone stay if I carry on talking?
Yeah.
Okay, thanks, Abigail. So I'm going to carry on talking. Sorry about that. Guessing these times is a little tricky. So we're going to look at function definitions and function signatures, and I want to make a really important distinction here. Python function signatures are really expressive. There's a lot really rich. There's a lot we can express with them. but there's some terminology that makes it clear what we're talking about. Def foo x y equals 10. Here's a really simple function definition. It's called foo. It's two parameters, x and y, and it prints them. X is a normal argument and y has a default value. So the terminology we use, this is a required argument. It is not a positional argument. There's some error messages in Python are a little unhelpful on this. This is an optional argument or an argument with a default value, y. Y is not, it's an optional argument or an argument with default value. It is not a keyword argument. Positional and keyword arguments are about the calling convention, how we call functions. This is about the function definition. X is a required argument, Y is an optional argument, or an argument with a default value. So let's look at optional arguments. They are fantastic, a really nice language feature. We have some read prices function, which is reading in a prices CSV and producing a dictionary, some data structure for it. And at some point, we need to extend the API. We want some additional debugging information. If we add the parameter like this, now all the existing uses of our code, all of the places that do read prices, prices.csv, they're now broken. There's this additional argument that we need to pass in. So when we extend, refactor, whatever, read prices function, we can add the new parameter, put a default value. The default value will be false with debugging off. It's an optional argument. It has a default value. You don't need to pass it in. But all the existing uses of the code carry on working just as they did before. But where you want additional information, we can pass in this additional flag. So if you're adding default values, they have to be the last parameters. All of your required arguments have to go first. So these are functions with optional arguments, straightforward, yeah. Now, when we come to calling a function, let's have read prices, but let's imagine it's always had this API file name, debug, file name, debug. Let's say this has always been the definition. We're going to call this read prices, prices.csv, true. These are positional arguments. They're arguments passed in one after the other by position. These are arguments passed in by keyword. File name equals. So these are keyword arguments in the function call. And because we're doing them by keyword, the order doesn't actually matter. These are all valid ways to call that function. So for this function definition, if you're coming and you're reading the code, prices, read prices, prices.csv, it's fairly obvious what that does, right? You're looking at that and you're thinking, I can probably tell what that does. It's reading a CSV file. That's a CSV file. It's reading a prices file. That's probably the data source. But this true, this Boolean flag, what does it do? It's very hard to tell from this code. However, if we pass this argument in, we can use mixed required and optional arguments, or required and mix of positional and keyword arguments in. This code is much easier to read. The purpose, the argument, this is why your argument names, your parameter names are part of the API of your functions, and you need good, clear parameter names, ideally. A bit easier said than done sometimes. So this mixed style, using keyword arguments to pass in the optional flags, makes your code more readable. But notice They were both declared as positional arguments in the functional definition. How we define the functions is orthogonal to how we call them. Read prices, file name, debug equals false. This is how we might declare it. File name, debug. Read prices. File name is a required positional argument. Debug is an optional argument, but I can pass it in. I can pass it in by position, or I can use. This is how I call the functions is orthogonal to how they're defined. So in the function definition, this is a required argument. This is an optional argument or an argument with a default value. In the call, this is a positional argument. This is a keyword argument. That's the terminology. It's really nice to be clear on. And finally, we've got 8 minutes left. We can do some more stuff. But that is not the whole truth. Yeah, always use short, meaningful names. That's really easy to do. Python function signatures are even more complex than this. We now have positional only and keyword only arguments. And they were added to the language. If I do help on sum, you can see, look, the first argument is iterable, and then we've got this funny slash. And actually, you can't pass the first argument by keyword. It's a positional only argument. And that's what Guido wanted in the language. So the way you express that, we have iterable. And this is the syntax. And then there's so now I've overridden sum, iterable equals 1, 2. That's a positional only argument. You can't pass it in by keyword. There's also the star for keyword only arguments. Sometimes you've got some function like this, star args, but you still want one star quad. You want to collect together arbitrary keyword arguments. Let's see if right, there we go. It has to be at the end. I can't select text at the in the interactive interpreter. There we go. See? There are no positional arguments. And configure has to be passed in as a keyword argument. There we go. So introduced as recently as Python 3.8, we have both positional and keyword only arguments. And the last thing I think I will touch on, tuple unpacking. Functions can return a value. If they don't return anything, there's an implicit return none. A bare return inside a function is the same as return none. And you can also, in your function, return more than one thing. And this 3,4, that's actually the syntax for a tuple. It's the same as this syntax. These parentheses are actually optional. So if we call point, what it returns is a tuple, but we can do tuple unpacking, and it looks and feels like we're returning more than one thing. And it's another lovely language feature and standard behavior of Python functions. And that, I think, brings to the end as much as I've got for you today. Any questions on any of that? I hope it wasn't too fast-paced.
What was the thinking about forcing only positional arguments in a function? Was there a I'm trying to think of a reason why you'd want to do that.
It really was because for years, the argument handling for functions written in C, they actually have to parse the arguments off the stack. So every function with its signature had custom C codes to do this. It was quite tricky. Larry Hastings, as one of the core developers, came up with a way of you put the function signature in the doc string in C, and he has this bit of code, a preprocessor called the argument clinic, a name from Monty Python, that will take that doc string and then generate optimized argument parameter handling code for you. And then he applied that all across the standard library. So now we have much better, much more consistent parameter handling. However, in order for that to work, we needed valid Python syntax to be able to express these positional only and keyword only arguments that were already in the language in C. Some you've never been able to do, some iterable equals. You've never been able to do that. It was written in C. So in order for the argument clinic to work, we needed a way to express positional and keyword only arguments at the Python level. So that's specifically why they were brought into the language, but also because Guido thought that they were a potentially useful feature. Why shouldn't we be able to do this? If it's useful in the built-ins, then other people might want to create similar APIs.
Sure. Okay. And that was the 5-minute argument, presumably. So, Monty Python.
That's right. Yeah. And does right? Any other questions? I'm going to be doing these every month, varying topics and degrees of difficulty. Thank you very much. See you all around.
Cheers, Michael. Thank you very much.
Thank you.
Thank
Bye-bye.
you.
Thank you.
Thank you.